This last section in chapter 11 is about molecular orbital theory. It's often abbreviated MO theory. This calculates orbitals for the entire molecule instead of just for atoms. So we just finished looking at valence bond theory where we hybridized orbitals on a given atom. This is going farther, and it's kind of hybridizing them over the entire molecule. This Schrodinger's equation cannot be solved exactly, so they use a trial function as an educated guess and see how close that is, and then they tweak it and go around and around and around in this iterative method to find the best function with the lowest energy. So we're trying to imitate nature, but nature is much better than we are. And so we're never going to get the perfect orbital, but we can get close enough. And really what's important about molecular orbital theory is understanding the big idea behind it, because the concepts of delocalized orbitals over an entire molecule are very important in organic chemistry. But to do that, we have to talk about some details. So these are called linear combination of atomic orbitals. So you could think of it as a weighted linear sum of the valence atomic orbitals of all the atoms in the molecule. So again, we're using all the atoms in the molecule, and then these LCAOs are delocalized over the entire molecule, unlike the hybrid orbitals from valence bond theory, which are located on a single atom. So let's look at the simplest possible molecule, hydrogen, H2. So here's one hydrogen atom. It has a 1s orbital, and the other hydrogen atom has a 1s orbital. Now, if we combine these, we can get a bonding orbital, and this bonding orbital is lower in energy than the original two orbitals, and that is given the name sigma because of its shape, like a sigma bond, right? It's symmetrical. You know, if you look at the end of it, it's, you know, so it's like a hot dog or something. It's round, right? Symmetrical. So we can add those two that way. We can also add them in a negative phase, which is like subtracting. So orbitals have phases, just like waves have phases above and below the node line. So this is like subtracting these two, and this is going to give us an antibonding orbital, which is higher in energy than the original orbitals. We can also think of this as this is destructive interference, and this combination is constructive interference of two waves. Okay, so this will give us a lower energy and facilitate bonding. And when we have the destructive interference, it's going to have a higher energy. And we see there's a big node right between those two atoms. And so this is obviously not going to be promoting bonding. It's actually working against that. So we can combine them with destructive interference and get an antibonding orbital. So this is called sigma star. The star means it's an antibonding orbital. And here's combining these with constructive interference. So this is a sigma bonding orbital. And so this is sigma 1s because it's a combination of 1s orbitals, sigma star 1s. So here we have high electron density between the nuclei. So this promotes bonding. Here we have a place of 0 electron density between the nucleus. Any questions so far? It's kind of weird. So instead of drawing pictures, we can draw orbital diagrams, but now they're molecular orbital diagrams. So what we've got here is the orbital diagram for one hydrogen atom, and here's the orbital diagram for the other hydrogen atom. These are the same as what we've been doing so far. You look at the number of valence electrons and you stick them in. So here, when we combine these two orbitals, the 1s orbital, there's two possibilities. There's one that's lower in energy, that's the sigma 1s, that's constructive interference, and destructive interference, or subtracting, gives us an antibonding orbital higher in energy. And so this is the sigma star 1s. So we look at those combinations. These are the molecular orbitals are available. And again, we started with two orbitals. We end up with two orbitals. You could say conservation of orbitals. And then we're going to take the electrons, there's one from each here, and we're going to fill in the molecular orbitals using the same ideas we did before, which is regular atomic orbitals. You fill the lowest ones first, up arrow first, singly if there's multiple orbitals, and then you pair up. And so this will get us two electrons in this bonding orbital. Something called the bond order. This is for diatomic molecules, and we're only going to look at diatomic molecules. This is the number of electrons in the bonding orbitals minus the number of electrons in the antibonding orbitals divided by 2. So if we look back at this picture here, this is a bonding orbital. There are 2 electrons there. So number of electrons in the bonding orbitals. And then we're going to subtract any electrons that are in the antibonding orbitals, because those are working against the bond. And then you divide by 2. So we have 2 in the bonding orbital minus 0 in the non-bonding or antibonding divided by 2. So this is a bond order of 1. If the bond order is positive, a chemical bond will form. The larger the bond order, the stronger the bond. If the bond order is 0 or negative, a bond will not form, because that indicates that the energy of the bonded molecule would be higher than of the individual atoms, and so that's just not going to happen. If we look at a diatomic helium molecule, so 2 helium atoms bonded together, they also have these 1s orbitals, and so when we combine these to make molecular orbitals, we get the same result for molecular orbitals, a bonding one and an antibonding one. Now we have 4 electrons, and so those will fill this lower one first, and then they'll go up here. And so if we look at the bond order, it's the number of electrons in the bonding orbitals, that's this one, so 2, minus those in the antibonding, 2. So 2 minus 2 is 0, divided by 2 is 0. So this has a bond order of 0, which predicts that this molecule never forms. And that's true, it doesn't form. Now we're going to look at some very strange diatomic ions here. So an He2 plus ion, that would be a helium atom and a helium plus ion is missing 1 electron. So now we have 3 electrons, so 2 go into the bonding orbital, and there's only 1 in the antibonding orbital. So if we're calculating the bond order here, we have 2 in the bonding orbital minus 1 at quantity divided by 2, which gives us a bond order of 1/2, which predicts that this does exist. It does. It's not common, but you can get it to form. The idea here is there are more electrons in the bonding orbitals than in the antibonding orbitals, right? So we are approximating the molecular orbitals as linear combinations of atomic orbitals, taking the standing waves that the orbitals essentially are and adding them together constructively and destructively to see what happens. We're always going to get a bonding orbital and a higher energy antibonding orbital every time we combine two atomic orbitals. We're going to fill the lowest energy molecular orbitals first, and we're going to follow Hund's rule. They get their own orbital until they need to pair up. And to have a stable bond, you need a positive bond order, which is more electrons in bonding than anti-bonding molecular orbitals. So use molecular orbital theory to predict the bond order in H2+. Is the H2+ bond stronger or weaker than the H2 bond? Now, the good news is that there will be some, bad news first. There will be some questions about this on the next exam. The good news is I'll give you the molecular orbital diagram, and you just have to fill it in. Okay, so it's not that horrible. So what you would start with here, no, not like that. Okay. So here's one hydrogen, and here is the other hydrogen. Now this is H2+. So how many electrons do we have here? Just one, right? One of these is the hydrogen, and this one must be the H+, has no electron. So when these combine, they make a bonding orbital and an antibonding orbital. So this is sigma 1s, and this is sigma star 1s. Energy is increasing up, as always. So we have a total of one electron. So these are the molecular orbitals in the middle, and these are the atomic orbitals. That's supposed to be an O. Use your imagination. So I'm going to take that one electron and put it in the molecular orbitals. It's going to go in the lowest one first, right? So we'll put one electron in here, and we're done. Wow, right? So that is the molecular orbital diagram. Now they're asking us to predict the bond order. Bond order is the number in bonding orbitals, which would be 1, right, this guy, minus the number in antibonding orbitals, which is 0, and then divided by 2. So this is going to have a bond order of +1/2. So is this stronger or weaker than an H2 bond? It's weaker, because the H2 bond, in the H2 bond, we have 2 electrons in bonding orbitals. 2 minus 0 divided by 2 is +1, and so that's stronger. The H2 plus bond is weaker. So looking at the period 2 homonuclear diatomic molecules. So these are diatomic molecules where you have 2 atoms of the same element. So again, we're looking at valence electrons here. So we did the period 1, now we're on period 2, lithium 2 molecule. So here we have lithium atom and another lithium atom. These electrons are in the 2s orbitals. They combine and they form molecular orbitals just like the 1s, except this is a sigma 2s and a sigma star 2s. And we have these 2 electrons, we stick them in there, and this is also going to have a bond order of 1, right? 2 electrons here, minus 0 divided by 2 is a bond order of 1. Here's beryllium 2. So beryllium has, like helium, has 2 electrons in the s orbital here in the valence shell. And so when we put all these 4 electrons in here, we get 2 in the bonding orbital and 2 in the antibonding orbital, and we have equal numbers bonding minus antibonding is 0, bond order is 0. So this is predicted to be unstable. Excuse me. Well, now we're going to get into the p orbitals. So, of course, that's a little more complicated. So, to look at boron, so here we've got the 2px orbital and the other 2px orbital. And each of these p orbitals, one lobe is one phase and the other lobe is the other phase. So here, red is a positive phase and blue is a negative phase. So if we add these together so that like phases are being added, that's going to make a bonding orbital, which is lower in energy. And if we subtract them, essentially we're taking one of these and turning it around to add, which is kind of like subtracting, then we're going to get something like this where bond density is away from the two nuclei. And these are also sigma orbitals, because again, if you look down the end of this, it's symmetrical. It's round like an O, like an omega, a sigma. The other two p orbitals are going to be parallel to each other. So here we're looking at the py orbitals, and they can be put together in phase to get something like this. This will be a bonding orbital. Now this is called a pi orbital, much like the pi bond, right? It's got these two pieces, right? Kind of like a pie. Now I want pi. What am I doing here? Okay. And if we add them together in a destructive way, then we have a big node between the two nuclei, and we've got the electron density on the outside. So this is a pi star. And then there's two other ones. These are vertical in the z-axis, and they're going to form the same two shapes that the py did, because they're parallel. And so we're just looking at it from a different perspective. And so here we have the bonding orbital, and this is an anti-bonding orbital. Does that make any sense? I always wonder. I stand up here and I'm like,
I have a question about the next part. So I can tell the difference between antibonding and bonding, but how do we know how many antibonding and bonding molecules there are in it?
so each time you combine two atomic orbitals, you get one bonding and one anti-bonding.
Okay.
Yeah.
I just was getting lost when you were filling the diagram.
Yeah, it is a bit confusing. So this, this is considered the regular order. So this hopefully looks a little familiar. We've got our 2s, we've got a sigma and a sigma star. And when we combine the three p orbitals, when we combine two of them, they'll make a sigma orbital, and the other two will make pi orbitals. And so we'll get a bonding sigma and two bonding pi's, and an anti-bonding sigma and two anti-bonding pi's. We started with 3 and 3. We end up with 6. Half are bonding, half are anti-bonding. What's different between these two diagrams is the order of them. So here, the ones on the bottom are switching places. This has the pi bonding as the lowest, and the sigma bonding next. Here, sigma bonding is the lowest, and pi is next. So what's going on there? Well, the relative order there is not the same for all molecules. They determine it computationally. For our purposes, boron, carbon, and nitrogen are going to be different than everything else. So, come on. So this is what we expect, and this one is for boron, carbon, and nitrogen. So BCN, be careful now, this one's different, okay? But again, I'm not going to try to trick you with this on an exam. And I'm sorry it's like this, but it is. The reason has to do with an increased amount of mixing between the S and the PX orbitals. I don't think that's actually helpful to anyone. So here what we're doing is we're not showing the atomic orbitals on the sides. We're just looking at the molecular orbitals that we get from combining them. And we're looking at the rest of the period 2 molecules. So B2, C2, N2, O2, F2, and E2. So boron, each boron has 3 electrons, valence electrons, right? So we have a total of 6 here. So we go 1, 2, 3, 4, 5, and 6. So we calculate the bond order. There's 4 in the bonding orbitals. Oops, sorry, not this one. There's 2 in the bonding orbital here and 2 here, that's 4. Minus 2 is 2, divided by 2 is 1. For carbon, 2 more electrons are going to go up here. Its bond order is 2. Nitrogen, we're adding 2 more electrons, 1 from each atom, and it's going up here, and this bond order is 3. So as that bond order increases, the bond gets stronger and also shorter. When we go from nitrogen to oxygen, now the order of these 2 types of orbitals is shifted. So sigma is lower than pi. So here, when we fill this in, we've got, let's see, 2, 4, 6, 8, minus 2, divided by 2, so a bond order of 2. And then here, we've got 2 more in the anti-bonding orbitals, and so the bond order is going down. And when we get over to neon, all of these are full, which is an equal number of bonding and anti-bonding orbitals, and so the bond order is 0. And we can look at the bond energies and the bond length, and we see that there is a correspondence as the bond order goes up, the energy goes up, and the length goes down. So the reason we talk about molecular orbital theory at all is because it explains some things that Lewis theory and valence bond theory cannot explain. We know from experiment that oxygen is paramagnetic. Remember, paramagnetic has some unpaired electrons, and those can interact positively with a magnetic field. The Lewis model and the valence bond model do not show oxygen as having any unpaired electrons. So Lewis theory here, we've got this double bond, and we've got all these lone pairs, everything's paired up. This is a valence bond representation of the double bond between the 2 oxygens. And again, there are no unpaired electrons. If we look at the molecular orbital diagram, though, we see that the pi star anti-bonding orbitals, those 2 electrons are not paired. And that is why oxygen is paramagnetic, sorry. So I have a video. Let's do the long version.
So for wetjet prevents streaks and haze better than a mop. So love it or your money back.
Now, I've been using Grammarly for years. Now, the great thing is Grammarly is free and easy to use. It not only helps you check your grammar, but all.
There we go. So that's liquid nitrogen. If you get, liquid oxygen. If you get it very, very cold, it will condense into a liquid.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. And then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
So my bad, that first one was nitrogen, not oxygen. Using the liquid nitrogen to make liquid oxygen from regular oxygen gas. Crazy cold. I'm starting to run the oxygen through there, and it's getting really cold. And there's liquid oxygen. It took a while, but he made some. It's kind of got a blue color. That's the nitrogen. And kind of like you expect with water or something, it's just pouring right through there. Look what the oxygen does. What? It sticks. It gets trapped in that magnetic field. So the oxygen molecule must have some unpaired electrons. And valence bond theory can't handle it. Does not tell us why this occurs. What do you think? It's cool. It's actually extremely cold. That's what it is. All that cloudy stuff you see, that's actually water from the air condensing into like fog because it's so cold right there. That's not the oxygen itself. Let's see if I can keep it from playing. Okay, let's get the lights. I want you to fall asleep yet. Save that for later. Okay, so this question is asking us to draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. And compare this to the N2 molecule, and is N2 plus diamagnetic or paramagnetic. I do not feel like drawing that, so we're going to do this. We're going to use this one that's already drawn. So we're doing N2 plus. So how many valence electrons in N2? 10. Yeah, 5 and 5. So this is 10, and we have to subtract 1 for the positive charge, so we've got 9 electrons here. So you can put electrons in the atomic orbitals if you want to. I think it's easier to just count up the total of electrons and then start putting them in. So we're going to start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so to calculate the bond order, we're going to look at the bonding orbitals, which is this one, and this one, and this one. and see that we have 2, 4, 6, 7. 7 in the bonding orbitals. And this is the anti-bonding orbital. There's 2 there. So 7 minus 2 divided by 2. So that's 5/2, or 2.5, sorry, 2.5. Okay, yes?
This is N2. Aren't we supposed to use the other one?
Yes, we are. We are. Man, I wish I could say I did that on purpose. I did not. Yeah. Okay, but let's compare and see how it's different now.
Okay.
Yeah. Oh, good grief. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's our anti-bonding orbitals, and our bonding orbitals. So that's going to give us the same bond order result, right? So the bond order is still 2.5. On some of these ions or molecules, this switcheroo here is not going to affect anything. But for other ones, it will affect them, like making their bond order different possibly, or more likely changing whether they're paramagnetic or diamagnetic. So this is a bond order of 2.5. The bond order for nitrogen, N2, would have 1 more electron here, right? It would have 10 electrons instead of 9. Is that going to make the bond order higher or lower? Higher, because we're adding to a bonding orbital. So nitrogen is going to have a higher bond order. It's actually 3. So that was one of the questions. And the other question is N2 plus paramagnetic? Does it have any unpaired electrons? Yes, it does. Okay. So I will give you, on the exam, I will give you a diagram like this, and I'll actually give you the correct one. And you'll have to answer some questions, picking out the species that has the highest bond order, or the one that's paramagnetic, or things like that. And so the procedure here is you look at whatever this molecular ion is, and you count the valence electrons just like we have been doing, right? If it's got a positive charge, you subtract an electron. If it has a negative charge, you add an electron. And then you put the electrons into this funky molecular orbital diagram in the same way that we put them into the atomic orbitals. So it's really different, and yet it's not. Let's see here. So now we're going to look at heteronuclear diatomic molecules. So here we have 2 different elements bonded together. So this is the Mo diagram for no. Oxygen's more electronegative, and so we show its atomic orbitals as being lower in energy than the nitrogen. But again, we've got s orbitals combining to form 2 sigmas, and we've got p orbitals, and we're making 2 sigmas and 4 pi's to our bonding, to our anti-bonding. So these contribute a little bit differently. I just don't see the point in even talking about that. Fluorine is weird. Fluorine is so electronegative that all of the atomic orbitals are lower in energy than hydrogen's 1s orbital. So here, if we're looking at hydrogen fluoride, here's hydrogen's atomic orbital, and here are fluorine's p electrons. The S is just so far down here, it's not going to come into play. And so this is going to make an even stranger combination. But again, this is predicting that NO does form. Use molecular orbital theory to determine the bond order of the FO minus ion. You know what? I don't even want to do that. Let's skip that one. So what about polyatomic molecules? So here, molecular orbital theory is going to fix this problem that we have with ozone. If we look at Lewis theory, we have the two resonance structures. We draw them like this, understanding that the true structure is between these. It's a combination. We know experimentally that each of these bonds is the same length. And so this must be like a 1.5 bond and a 1.5 bond, but we can't draw that with the Lewis theory. And we can't do that in valence bond theory either. We have to have a double bond here and a single bond there, or a double bond here and a single bond there. Neither of them explains how those two bonds are equivalent. In molecular orbital theory, what we get is molecular orbitals from all three atoms that get delocalized over the entire molecule. So this is representing the combination, the pi molecular orbitals. And so it gets delocalized over the entire molecule. And now we can see, oh, that's how ozone can have two identical bonds, even though we see that there's essentially 3 bonds split in 2, right? Any questions? This one's very important for OChem. So this molecule is benzene. It has a 6-carbon ring, and in Lewis theory, we draw this as alternating double and single bonds. But we understand that this has resonance, so the 2 resonance structures, and this is more like what it really looks like. That second bond here is stretched out around the entire molecule. So we have the double bond here, here, and here. Those 3 double bonds are actually stretched out around the entire molecule. And so all of the bonds are equivalent. And so we need to understand enough of molecular orbital theory that when they tell us stuff like this in OChem, we're willing to believe them.